This video is for lesson 24-2, Theorems about chords. Learning goals are to describe relationships among diameters and chords of a circle, and to prove and apply some theorems about chords in a circle. The diameter of a circle and a chord of a circle have a special type of relationship. Let's investigate that below. So in question 1 it says draw a diameter. It doesn't say where to draw it. So let's just draw one that goes across the circle through the center horizontally. One endpoint is here and the other endpoint is here. This is a diameter. Now let's draw a chord that's perpendicular to the diameter. So our chord has to cross the diameter at a 90-degree angle. Doesn't matter where we draw it. I'm going to choose to draw right down here like this. This chord touches the circle at this endpoint and this endpoint. Remember, we were told to draw this perpendicular, so there's a 90-degree angle where they intersect. Now we're asked to look for a relationship in this picture. Specifically, let's look at the length of this part of the chord from the dot to the point of intersection, and look at the length of this part of the chord from this dot to the point of intersection. What do these distances look like to you? These distances look equal. We could conjecture that when a diameter is perpendicular to a chord, that the chord is split into two equal parts. A good vocabulary word to use is that the chord is bisected by the diameter. If we're then able to prove that conjecture, it becomes a theorem. We're not going to take the time to prove it, so let's just accept that this is a theorem and then do problems using this theorem later in the class. So let's write out the theorem that is shown in this illustration. When a diameter is perpendicular to a chord, it bisects the chord. Please write that down in your notes. Let's go to the next page and look at another theorem that involves chords. In a circle, two congruent chords are equidistant from the center of the circle. In this drawing, we can explore what that theorem is talking about. Here we have a drawing of a circle, and there is a chord drawn called chord AB. Somewhere else, there's another chord drawn. It is chord DC. These chords are drawn so that they are congruent. They're the same length. When chords are congruent, what we know to be true is that they're the same distance to the center of the circle. What that means is that the distance from R to Y is the same as the distance from R to X. Again, we're not going to take the time to prove this in the lesson. Let's just accept that this can be proved, and then we can use this theorem to solve problems. Let's look ahead to the check your understanding questions. Number 6. A chord of a circular clock is 12 inches long, and its midpoint is 8 inches from the center of the circle. Let's draw a picture of that so we can visualize what it's talking about. So we have a circular clock, so our best circle that we can draw freehand. Right in the center is a dot, that's the center of the circle. We're told that there's a chord 12 inches long, and that the midpoint of the chord is 8 inches from the center of a circle. So it doesn't say where the chord is or anything, so let's just draw one in someplace. Maybe it goes from here down to here. That chord is 12 inches long. The midpoint of the chord, so a dot right there in the middle, is 8 inches from the center of the circle. We can label that with 8. We know that if this is the midpoint of the chord, that segment from the center that's touching the chord is perpendicular, and we know that's a 90-degree angle there. If the chord was 12 inches long, we know that this piece is 6 and this piece is 6, again because this dot is the midpoint. Now what are we asked to figure out? Question A, what theorem can you use to determine the length of the radius of a circle? Well, we don't have a radius drawn in our picture. Let's draw one in there from the center out to the edge of the circle. Now instead of just drawing randomly, let's draw our radius so that it goes from the center to one of the endpoints of the chord. That way we create a small right triangle, and that would be helpful to us if we ever needed to figure out how long the radius is. What theorem can we use to determine the length of the radius? We can use the Pythagorean theorem. Let's find the radius. So the red line, the radius, is the letter C with the Pythagorean theorem. This side here is the letter A, and the 8 is the letter B. So we can go A squared plus B squared equals C squared. I'm going to pause the video for you to figure out how long the radius of that circle is. The radius is 10 units long. Now question 7. A chord of a circle is 15 inches long and its midpoint is 9 inches from the center of a circle. Calculate the length of the diameter of the circle. So this is a very similar question to what we had before. We have a circle. It always helps to draw pictures of things in geometry. Here's the center. We're told we have a chord that's 15 inches long. We don't know where the chord is. We can draw it anywhere we want. Going across the circle, that's 15 inches. We're told that the midpoint of that chord is 9 inches from the center of the circle. So let's just connect them together at a 90-degree angle, and we can label that short thing as 9. Now remember, the original chord was 15, so just this half of it is 7.5. And then this half here is 7.5. Question is, how long is the diameter of the circle? Well, let's draw the diameter. I want to draw all the way across the circle, but I'm not going to just draw any place at all. I want to draw in a way that allows us to use the 9 and the 7.5 to help us get the answer. I'm going to draw my diameter from this endpoint through the center across to the opposite side. Do you see the right triangle? One side is 9, one side is 7.5, and the hypotenuse could be given the letter C. When we find the answer for C, that will be the radius of the circle. What would you then do to get the length of the diameter all the way across? I'm going to pause the video for you to answer question 7. With the Pythagorean theorem, I get the radius of the circle is 11.7, and then for diameter, multiply that by 2 to find out 23.4 inches. Let's look for even another theorem that involves chords of a circle, because every new theorem we discover will allow us to solve problems about circles. So question 8. Using a protractor and a ruler, draw a circle. Let's not actually use a protractor and a ruler, but just freehand this. So here is a circle. Let's draw chord AB and chord CD so that they intersect. It doesn't say where to draw them, so maybe this is chord AB. Here's A, here's B, and then somewhere intersecting it, we'll draw another chord, CD. Again, I could have drawn these chords anywhere I wanted, any length I wanted. I just wanted them to intersect each other. So right here, this dot is where they intersect. In the directions it says label that intersection point X. Okay, there it is, X. Notice that when you have intersecting chords, this creates 4 parts or 4 segments. I have 2 shorter segments up here near the top of the circle, and then these other 2 segments are longer looking than those 2. Now we're asked to measure these with a ruler. Again, let's not actually measure these with a ruler, just make believe that we have. Then let's look at the product of segment AX and segment XB and compare it to the product of segment CX and segment XD, and what do we notice? Well, if we had measured them, we would notice something. Let me put some fake measurements on there so that we can explore this. Let's make believe that AX turned out to be 2 units long and CX turned out to be 3 units long with a ruler. And let's say that on a ruler, XB turned out to be 6 units long and XD ended up being 4. If we find the products as described here, what do you notice? Well, AX is 2 in our example, and XB is 6. the product is 12. CX is 3 and XD is 4. The product is 12. What we notice is the products are equal. Again, let's not actually prove that that's true, but just accept that it can be proved, and that gives us another theorem. Here's the theorem for you to write in your notes. When two chords intersect, the product of the parts of one chord equals the product of the parts of the other chord. Let's jump ahead to the check your understanding number 10. In the circle shown, what is the measure of x? We talked about several different theorems involving chords today. Which of those theorems fits this situation? We have two chords and they intersect. Well, this is that very last one we talked about. The product of the parts of the chords are equal to each other. So x times x is equal to the 4 times the 49. X times x is x squared, and 4 times 49 is 196. Now let's do the square root to get the answer for x. The square root of 196 is 14. So we solve for x using one of the theorems that we talked about today. So in today's lesson, we discussed different theorems that involved chords, and knowing those theorems will allow us to solve different problem situations that involved circles. One of the theorems we talked about was if you have a circle and a chord ends up being perpendicular to the radius of a circle, then that chord is bisected. That would allow us to figure out how long parts are in the circle. Another theorem that we looked at was if there is a circle and there are two chords in the circle that are congruent to each other, then those chords have to be the same distance to the center of the circle. Like if that was 3, then how long's this? It's also 3. Another theorem that we talked about has to do with chords intersecting in a circle. So if this is a chord and this is a chord crossing through it, then this part times this part is equal to this part times this part.